Okay, so this is the problem we're going to be solving. Let's look at what we have here. We've got the t derivative of u is equal to k squared times the double x derivative of u minus c times the x derivative of u. So I'm just going to make a little comment here in the solution. Of course, you wouldn't have to do this in your solutions, but I just want to mention it. So this is really, I'm going to, what do I mean by this? This is really two PDEs in row one. Um, by which I mean PTU equals k squared, pxxu is the diffusion equation. If we look at PTU equals equals c xu, we can write this in conservative form, px just c times u. This is a conservation law. Call that the given PDE was derived as a diffusion process along with a convection process. Okay, so diffusion is spreading out, convection is moving it along. So it's like put a drop of dye in a river, or put pollution in a river, and the currents are taking the pollution along. As the currents are taking the pollution along, the pollution is spreading out, but the currents are also taking it along. So there's two things going on. So I'm going to give, so given that, we can kind of guess at what a form of what the solution might be. I'm going to give two solution methods. One is just going to be using straight up Fourier transforms, and the other is going to be using this intuition. So let's see if subsection will work in an answer. Solution one, Fourier transforms. Let's see, will this work? Looks like it. Okay, but I'm going to make it a star so there's no number. Okay, just going to take Fourier transforms at both sides. Now, I'm not going to take a very long time to do this part. I'm just going to probably write this all out in one line. On the left-hand side, we're going to have the t derivative of u. I'm going to write I feel like writing the argument. Maybe we'll see how it goes. On the right-hand side, okay, we're going to have minus k squared, minus k squared, c squared, u. And then it's going to be, okay, so look, if I look at look at the x derivative, it's going to be minus, so it's I to the power of the order of derivative, so I to the power of 1, times c to that power, so c I, c I x I, there's a lot of so obviously C, the letter Charlie, and the Greek letter Xi sound a lot alike, and I've got I's in the LaTeX and X's in the LaTeX. It gets kind of confusing. Okay. Again, I just took Fourier transforms at both sides. This is an ordinary differential equation, but I'm going to sort of combine it into, I'm going to combine the right-hand side. I'm going to factor out the Fourier transforms. And so we're going to have minus k squared c squared plus ci c times the Fourier transform. Okay, and as far as the variables t is concerned, all of these k squared, c are all constants. So what we have here, the solution to this equation, it's just going to be the Fourier transform evaluated at c and t is equal to 0 times e, and it's going to be to the power of that times t. So minus, so I could just put the whole thing, I don't know why. That, like that, times t. I'm probably going to have to reformat this. Yeah. let's just do it like this. This is an ODE, and the solution is, okay, but of course, this part, that is just the Fourier transform of the initial data. Okay, let's see how this looks. Okay, and now I want to use the Fourier transform line in the book that has the e to the I part. So I'm actually going to break this down a little more, and I'm probably going to need, therefore, another line. So this is going to be e to the power of minus ci. Let me write it this. Ci. No, I want to write it like this. Ci. Okay, that, and then this, and then e to the power of minus k squared, like this. Okay. All right, there, that's what we have. And so I know what I can do here. I know basically more or less how to find the inverse Fourier transform of that. I know that I've got a product of two Fourier transform, or I've got a product of two Fourier transforms then. And so to find the original one, to find the original Fourier transform, I'm going to do convolution. And then I still have to figure out what to do with this part. So the inverse Fourier transform of this part is, okay, so it's going to be a convolution. So it'll be minus infinity to positive infinity f of y, and then the inverse Fourier transform of this. Now I've got the k squared, so in the book it typically uses alpha, but I use k squared, so this is going to be 1 4 pi k squared t and power of minus frac. So now we'll have the x minus y squared. And here we go, 4 k squared t dy, and actually since we normally do it, I'm going to put this on the outside of the integral. Okay, so there's a line in the Fourier transform table. It's very hard to see, but there is a minus sign there. You'll be able to see it better when you look at the document. Okay, so there's a line in the Fourier transform table. Now we're going to use, that's what I'm about to write here. Actually, we even had this as a homework problem, if you remember. If I look at the Fourier transform of, so using the fact that the Fourier transform of g of x minus c is the Fourier transform of g times, I'll write it out like this, times e to the power of minus c. I realize I've made a typo up here. Minus, so did I get this right? We have, and I have a typo up here. When I factored this out, there should have been a t, because there's a t here. I factored that out. There should have been a t there. Okay. 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 So now, what do I have? I've got the e to the, imaginary number times this. I know the inverse Fourier transform of that. It's given by this right here. So then the inverse Fourier transform of this is going to be the inverse Fourier transform of that, but shifted to the right, c times t units. So I'm going to copy what I have here. And now wherever I see an x, I'm going to put an x minus ct. Okay, so let me compile that and we can see what it looks like. Yeah, so this is what we have here. And so notice what's happening. It's just the solution is just this solution, but translated to the right ct units. And so this makes sense. Well, it's not supposed to be y, that's supposed to be a t. This makes sense because what is this modeling? It's modeling the diffusion equation that's being moved along at c meters per second. So the x minus ct is like, it's the diffusion process, it's the solution to the diffusion equation, but this is also moving at c meters per second, and so after t seconds, it's going to be moved along ct units to the right. Okay, solution method 2 is basically just a guess that this is what the solution is going to be. How can we do that? We're going to use intuition about what it's actually modeling. Okay, so the PDE models a diffusion process that is being moved along at a rate of, I'm just going to write c units per second. Okay, the time units don't even have to be seconds, but that's the idea. It's moving at a rate of c units per second. Okay, so our prediction is that u of xt is going to be equal to the solution to the normal diffusion equation, but just shifted to the right ct units. So it's going to be x minus ct, sorry, I'm going to write v x minus ct, comma t, where v is just the solution to the normal diffusion equation. So where v satisfies squared pxxv. Okay, but here's the thing. So this is a good argument, but it doesn't really, like, that could be wrong. What if, so one of the important things here is that the diffusion process and the convection process are kind of happening independently. Well, that's correct. I mean, that's how this is modeling it, but maybe our model picks up on some interaction that we're not sure of. So what we need to do now is actually verify that the solution that we are getting actually satisfies the PDE. So let's verify this. To verify this, we're just going to compute derivative. So the t derivative of u of xt. Okay, so we're going to have to use the chain rule. This is going to be equal to the the x derivative of v times the t derivative of that. So that's going to be minus c px v plus it's going to be the v derivative. Where am I here? It's going to be the v derivative. Sorry, the v derivative. The t derivative of this of v times the derivative of t, which is just 1. So this is plus pt v of x. Where am I here? X minus ct, comma t. Okay, so we're getting x minus ct, comma t. Okay, so what's happening here? Well, minus cxv, or minus c times the x derivative of v. That's good, we have that. But now, what do I know? So here's where something interesting is going to happen. What is the t derivative of v? Oh, sorry, there's supposed to be a u here. No, that's right. Okay, so what is the t derivative of v? Well, the t derivative of v is just equal to k squared times the x derivative of v. So this is equal to minus c pxv plus k squared times the x derivative of v, or times the double x derivative, the double x derivative of v. And how do we know that? Because it satisfies that equation. Okay, but this is just equal to the k squared times the double x derivative of v minus c times the x derivative of v. So v satisfies the PD. So really, this is just a sort of chain rule exercise. Okay, but we know that. Wait, what is it? Oh, sorry. I need to, let me just go back here a little bit. The x derivative. So what is So let me be a little more careful about this. X minus ct, comma t, down here. Let me put the arguments for v here. Okay, so now what I meant going from this line to this line, this is the double x derivative of u of xt, because that's what that is. And then this, well, that's a weird typo. That's a c, and this is the x derivative of u of xt. Okay, so we already know that v of xt is equal to, okay, I'm just going to use this solution up here. I'm actually going to need this on a new line. So, and then we'll have the same conclusion about u of xt, so I can just rewrite it there. Okay. Two ways of thinking about it. One way is kind of an intuitive way of thinking about it. I like that way, but it requires a little bit of thought. And the other one is just doing Fourier transforms. That also requires a little bit of thought. So I guess either way, you're going to have to be thinking about it, which is probably not so surprising. Okay, that's it for this problem.